Hello to everyone who's watching this video. My name is Hao Zheng. I'm currently a PhD student in the University of Pennsylvania School of Design. My research topic is mainly about machine learning and its application in architecture design. I'm glad here to present our paper, Architecture Layout Design through Simulated Annealing Algorithm, in cooperation with Yue Ren from University College London. Metropolis algorithm is designed for finding the minimum or maximum value of a function. Rather than recursively comparing values in a function and finding the direction of optimizing to reach the objective value, in Metropolis algorithm, there is a certain possibility that the program will accept a worse result in its optimizing direction, so that the optimizing process will not get trapped in a local optimum. Simulated annealing is an algorithm based on Metropolis, which changes the variable t into a process-related variable. It decreases gradually so that the possibility of accepting a worse result will become smaller and smaller, and finally reach a stable status without any acceptance to the worse result. This process is similar to the physical annealing, where the variable t acts as a temperature value to control the annealing rate. So it's called simulated annealing. The application of simulated annealing includes a variety of research domains. For example, for arranging timetable to avoid conflict, for transforming a bubble diagram into a plan design without gaps, and for optimizing the structural elements to save materials. Different from the previous research, this paper focuses on the simulated annealing algorithm in arranging buildings in a site, especially for residential areas planning, developing unique functions to describe the main aspects when designing architectural layout, optimizing and making a balance between each design focus. Through this research, we want to provide useful tools for architects that the layout of the residential buildings can be generated by controlling the parameters of the design tendency, thus solving an example of translating design ideas as strategies into parameters with a more mathematical method. To clarify the quotient and working limit, parameters to represent the condition and requirements of the design were proposed firstly. For the site, when designing, all parameters are already set and cannot be changed. Parameters include P_ent for the position of entrance, J_bow for the boundary geometry of the design area, A_sun for the local sunshine angle in the winter solstice, and J_ref for the geometry of the river or any landscape attractions. These four parameters stay constant and will be used to define penalty and reward functions. Then the building, which needs to be placed into the site. Parameters include Jn for the boundary geometry of each building, Pn for the entrance position of each building, Hn for the height, An for the rotated angle, Xn and Yn for the relative position of each building. Among them, J, P, and H are pre-designed and should keep constant, while X, Y, and A are the main parameters, which will be fed into the simulated annealing algorithm as X value for the objective function. After defining all parameters, the objective function fx was developed as the weighted sum of 6 subfunctions. First, in order to avoid any obvious geometric errors, 2 penalty functions were proposed. One is out-of-boundary penalty. When the geometries of buildings are partly outside the site boundary, a minus point will be added into the objective function based on the outside areas. Also, when 2 buildings have an overlapping area, it doesn't make sense. Thus, another penalty function is overlapping penalty, which adds a minus point based on the overlapping areas to avoid the collision of geometries. In the two formulas, K1 and K2 are factors that adjust the order of magnitude. In addition to the penalty function, 4 reward functions were also constructed to guide the system to find the best solution. First, if the entrance of a building is close to the entrance of the site, the system will give a reward point to the function because it will be convenient for the building users. It's called a convenient reward. The shorter the distance between two entrances, the higher score you will get. While K3 acts as a coefficient, L3 is the minimum limit for the distance, protecting F3 from becoming too large. Also, a traction reward was built, representing the landscape value in the site for each building. The system will find the closest point from the curve of the river to the center point of the building and calculate the distance between 2 points. Then the angle between the normal of the rival at that point and world vector x will be figured out as a rive. By comparing a rive with AI, the orientation of the building facing the landscape will be evaluated, and the length of the boundary of the building will also be taken into account to represent the possible length of the areas that the users can see the landscape from the building. The third and fourth functions are both about sunlight, since all buildings are initially modeled in the world coordinate, in which positive y unit towards the north, and the balconies are always in the southern part of the building. The only face that can receive direct sunshine is the southern curve in the geometry. Therefore, the orientation reward was proposed, indicating that if the building is facing south, as it originally is, additional reward will be given to the evaluation function. Also, there are always shadows for each building, which may block the sunshine of other buildings. The last reward function, sunlight reward, will be given to the evaluation function if the buildings are exposed to the sunlight in most of the daytime. To calculate the worst time period of receiving sunshine, the local sunshine area in the winter solstice and sun will be used to draw the boundaries of the shadows. Then, by calculating the percentage of the areas in the building which is not covered by shadow in each time period, the function will work properly to feedback a reward function between 0 and 1, representing the overall condition of daylight. Lastly, by adding all 6 functions together, the final objective function is completed. There are 6 coefficients, K1 to K6, adjusting the weights of subfunctions. Different settings of these six parameters may result in totally different optimals, showing the design choices from these different design requirements. First, K1 and K2 were always set as a very large number, so that once the geometric error happens, the penalty function will work in priority to drag the optimizing process back to the acceptable track. Then in Figure 1, the optimizing process starts from an initial status that all buildings are arranged in the center of the site. With a larger K3 value for the convenient reward in Figure 2, the buildings will gather near the entrance. When the attraction reward acts as a main road in Figure 3, all buildings are placed along the river and facing towards the nearest point in the river. While the orientation reward forces all buildings to keep zero rotated in Figure 4, other factors, the other factors like the attraction of landscape and entrance still works to construct the proper architectural layout. When the sunlight reward provides more bonus points in Figure 5, buildings tend to become more rotated, very precise in positions to avoid being covered by the shadows of other buildings. In Figure 6, a balanced consideration of parameters weights is applied to the objective function, so that all factors work together to generate a layout that building number 2 follows the convenient rewards, and building number 5 follows attraction rewards. Building number 1, 3, and 4 follow the orientation rewards, and the building number 6 follows the sunshine reward. Also, by controlling the temperature parameters in the simulated annealing algorithm, different results will be generated. A higher temperature means a higher possibility to accept the worst result. We can understand the variable T as the initial temperature and K as the maintenance rate of the temperature. The goal of the parameter turning is to find a stable setting of T and K to reach a larger F value. So after experiments, we found that a high T value with a medium K value performs best. It has higher possibility to provide a solution with larger F value. Thus, the recommended T and K settings are 100% and 0.95 in Galapagos in gas sulfur. So this is the animation when running the program with the balanced coefficients and better settings of the temperature. Also, we can apply the same framework but with different objective functions to solve other layout problems, for example, the interior layout. In conclusion, simulated annealing is a very powerful algorithm for finding the optimal solution with customized penalty and reward functions and proper settings of parameters weights. Architects can translate their own design ideas and strategies into parameters and easily use the simulated annealing to generate architectural layouts. Thank you for listening.